Hey everyone, hope everybody's doing well and getting your work done in all your classes. But today in chemistry we're going to be working on the combined gas laws. And combined gas laws are pretty much what it sounds like, where we're taking Boyle's law and we're taking Charles' law, and there's a third one that we haven't done any problems with called Gay-Lussac's law that relates pressure, volume, and temperature all in one equation. So if you recall from Boyle's law, they are inversely proportional. So we knew that pressure and volume, were side by side. And we knew that from Charles' law, that volume and temperature were directly proportional. So that means that it was V1 over T1. And if you take a look, we have a representation here where we relate pressure, volume, and temperature all together. Now, what the combined gas law says is that the starting pressure times the starting volume divided by the starting temperature is got to be equal to the final pressure times the final volume divided by the final temperature. So there's our expression. P1 times V1 over T1 is equal to P2 times V2 over T2. Now, again, this is in your reference tables if you need it. Also, you can see this in your notes. I'm going to write it over here on the left side using the getting rid of the equation. Basically, I'm going to cross multiply before I plug in any numbers. So what I have is P1 times V1 times T2, and that's going to be equal to P2 times V2 times T1. I know some of you don't like to work with fractions. That's okay. But what you got to be careful of, if you are using this expression over here, you've got to be very careful to make sure that you're putting the proper temperatures in your problem correctly, because it is P1 V1 times T2. That's a mistake that I see very often, and I hope that you'll practice enough that you're not going to do it. So let's do this first problem. Again, because now we're dealing with 3 variables, or really 6 variables, we need to make a key. So our key is going to be P1, V1, T1, P2, V2, and T2. And if you don't make the key, it's going to be very difficult for you to get these problems correct, just because it helps you to really keep things organized when you are making your key. So now we read the problem. A sample of carbon monoxide gas occupies 15 liters at 4 atmospheres of pressure and a temperature of 20 degrees Celsius. So that's our starting conditions. So our pressure is 4 atm from right here. 4 atms is our starting pressure. Our initial volume is 15 liters. 15 liters. And our starting temperature says 20 degrees Celsius. Now remember, we're dealing with combined gas law problems. Temperatures must be in Kelvin. So it's 273 plus 20 for a total of 293 K for our temperature. So that is 273 plus the 20 to get the 293. Just make sure you remember you've got to always do that with these combined gas law problems. Boy, this pen is like crazy. And then, of course, we need to fill in our variables for our final products, or the final conditions of the gas. So it says, what is the new volume? So that tells me right there that I'm solving for volume. If the pressure is decreased to 2 atms, so there it is, 2 atms, and the temperature is increased to 50 degrees Celsius. So remember, 50 degrees Celsius, I've got to convert that to Kelvin. So if I add 50 to 273, I get 323 K. 323 K is now my final temperature. So I'm going to solve this first problem here using our initial expression over here. So I'm going to rewrite the formula. P1 V1 over T1 equals P2 V2 over T2. So there it is. I'm going to plug in my numbers. My initial pressure is 4 atmospheres, so I can put it right here. My initial volume is 15 liters, put it right there. Notice that I'm keeping the units. We know that the units help us to solve our problems correctly. We can tell if we've made a math mistake if we don't have the right units when we're all done. But we have our 4 atmospheres, that's our initial pressure, times our initial volume, that's 15 liters, divided by our initial temperature, which is 293 K. And that has to be equal to, boy, yeah, that's a K. That has to be equal to our final pressure, which is 2 atmospheres. So we see our pressure is cut in half. We're looking for the volume, so that's going to be our V2, and then of course that is over our final temperature, which is 323 K. So now when we solve this, I've just got to solve for V2. So I'm going to take my V2 multiplied by my 2 atmospheres, and I'm going to multiply that by the 293K. So basically what I did here is I just cross-multiplied. Just like we solve any of these other problems, I multiplied this way. The reason why we're cross-multiplying and not multiplying across is because we have an equality here. If you think back to when we did the dimensional analysis problems, we were multiplying fractions. Here we're dealing with equalities, so one is equal to the other, so that's why we're cross-multiplying. Then that's going to be equal to my 4 ATMs times my 15 liters, I'm going to run out of space, times 323K. Oh, just made it. 323K. So now to get V2 by itself, divide this side by the 2 ATMs. Oh boy, what did I do here? I think I touched, yeah, there we go. I touched something over on the side of my screen here and it took away my pen. So there's the 2 ATMs. I've got to divide this side by 293K. So I divide that and I divide that. They cancel out, so I'm left with V2. But whatever I do to the left side, I have to do to the right side. So it's 2 ATMs times 293. And that's K. So now my ATMs cancel my ATMs, so they're gone. My K cancels K. I'm left with liters, which is what I would like to have when I'm all done. And now all I have to do is just do the math. So I'm going to multiply 15 times 4 times 323. Now 15 times 4 is 60, and 323 times 60 gives us 19,380. That's what's on the top, and that's liters. I have no units on the bottom. So it's 293 times 2. 293 times 2 is 586. No units on the bottom. So now my V2 is equal to these two numbers divided. And I have 19,380 divided by 586, and it comes out to 33.1 liters. So what you can see happened here, here's my answer, is that the volume a little more than doubled. It's hard to estimate these because you've got variables that are going both directions. But that's how we solve those. And I'm going to scroll up here and do this other problem. If you take a look, I got another problem here. And this particular problem, I'm going to solve using the other formula. Now the formulas are the same, they're just expressed differently. So this one's going to be, my formula is going to be P1 V1 times T2, and that is equal to P2 times V2 times T1. So there's the expression that we're going to use. Got to make my key. So right over here, I'm going to do my P1 equals, my V1 equals, my T1 equals P2 V2 T2. Now I know it gets tedious making this key every time, but it really helps to make sure that you're not going to make any silly mistakes. So just try to reinforce that good habit of making the key every time. So our initial pressure, well, let's read the question first. It says a gas has a pressure of 40 kPa, different unit, but it's still a pressure unit, at a temperature of 400 K and a volume of 50 milliliters. What will be the new pressure? So I'm going to be solving for my final pressure if the volume increases to 100 milliliters and the temperature is decreased to 300 K. So it's pretty straightforward. We're just going to plug in the numbers. So I've got 40 kPa for my initial pressure. And again, as long as I keep the units there, the numbers don't really matter. What it represents is pressure. So this is going to be equivalent to, a really low amount of atmosphere. So it's a pretty low pressure, but it doesn't really matter. It is a valid unit of pressure. So we'll just solve it with those. We don't have to convert it or anything like that. Our volume is 50 milliliters. And for this problem, if you take a look, our temperature is already in Kelvin, so we don't have to do that conversion. So it's 400 K. So that saved us a little time. Our P2 is what we're solving for. Our final volume, we can see it here, is 100 milliliters. And our final temperature, right there, 300 K. All right, so now I'm going to plug these numbers in. And we're going to start with our initial pressure. I've got 40 kPa. And again, I'm keeping the units in there so that I'm not going to make mistakes or silly mistakes. That's 40. That's pretty ugly, isn't it? Sorry about that. Let me fix that. 40 kPa. There you go. 40 kPa times our volume. And if we take a look at our V1 is 50 milliliters. Fill that one in. Now here's where it gets tricky. I am now putting my final temperature in, not my initial temperature. So I'm going to jump down here to 300 K because my relationship is now P1 V1 times T2. And then that's going to be equal to my final pressure, which is what I'm solving for. And I'm going to multiply that by my final volume, which is 100 milliliters. And that's going to be multiplied by my initial temperature, which is 400 K. And again, that's where most people make mistakes if they use this formula. I personally think it's easier because it's one less step you have to do in the math. However, you got to be very careful not to make that mistake of putting in the T1 for the T2 and so forth. So just be careful when you use this, if you use this method. So now we're just going to solve for the P2. So what I'm going to do is I'm going to take this side, I'm going to divide it by, to get the P2 by itself, 100 milliliters and 400 K. Whatever I do to that side, that cancels. I'm going to do to the other side. So now I've got my 100 milliliters and my 400 K. Units cancel. Units cancel. I'm left with kPa, which is what I need for pressure. And now I just do the math. I plug in the numbers into the calculator, or if you're really sharp, there's a lot of zeros in here. You can start canceling out zeros if you'd like, but the easiest way to do it is just to multiply 40 times 50 times 300, and you get 600,000. And of course, the only units that are left are the kPa. And then we're going to divide that by, this is going to be equal to our pressure, 400 times 100, just add 2 zeros to 400, you got 40,000. So that's 40,000. And then when we do the math, 600,000 divided by 40,000 is 15 kPa. And that's how we solve combined gas laws. So the plan is that we're going to be working on this. You'll have some problems to work on. And then again, like we did last with the Charles Law and Boyle's Law, you'll take a quiz at some point, maybe Thursday or Friday, depending on how things are going. But if you're having any problems, please feel free to email me. Have a good day.